concrete beams. This will include part one, and it will be introduction about the design of beams and all requirements and checks that you need to follow to design reinforced concrete beams. First of all, let's talk about different types of beams that you may see. You may see simply supported beams when you have only one span. It could be like simply supported like this one, or sometimes it could be also fixed from ends. In this case, it is easy to find the bending moment and design for reinforcement in this type. So the structural analysis of the simply supported is easier one. Then you may also see a continuous beam of two or three or more spans, as you can see. In this case, usually this type of structure is indeterminate structure, and the structural analysis is somehow more difficult than the previous case when you have a simply supported, but usually different codes are giving some factors that you can use to help you to find the bending moments, shear forces, and then you can use them to make your design. Of course, you also can use any computer program to make the structural analysis for you. The third type, it could be a cantilever. You may have a cantilever beam when this is a free end here. And also this one is similar to the first one, which is simply supported. Both of them are determinate and will be easy to find the bending moment, which is WL square over 2 or PL. And you can find also the shear and you can make your design. In the cantilever here, don't forget that the reinforcement should be, or the main reinforcement should be at the top because the tension will be at the top. And the simply supported, the main reinforcement will be at the bottom. For the continuous, you have some reinforcement above the supports will be top reinforcement, and in the spans, it will be bottom reinforcement. Also, you may classify beams into shallow beams and deep beams. Shallow beams, when you have the span to depth ratio is greater than 2.5. This is the span divided by the depth ratio is greater than 2.5. In this case, we call it shallow beams, and the design is based mainly on bending moments. Another type also you can see, which is called deep beams. In this type, the span over depth ratio is less than or equals 2.5. So you have big depths here compared to the span. In this case, the design is based mainly on shear forces. Also, you may see different types of beam, like we call drop beams, when you have the beam is here and supporting the slab, which is the slab in this case is above the beam, okay? So the slab is supported on the beam. Here we have the web is under the slab, and this is the famous types that you may see it in like most cases. Also, you may see something called inverted beams. What is the inverted beam? Inverted beam when you have the slab is at the bottom of the beam. Still, the beam is supporting the slab, but the slab in this case is at the bottom of the beam. You may see this type, which you call it inverted beam here, at roof plans when you have roofs and you want the roof to be smooth from the bottom. So sometimes you invert the beam and make it at the top. So we call this type inverted beam. Also, a third type is called hidden beams. Hidden beams, you may use a beam with the same thickness of the slab. You have a slab thickness here, and you have a beam with the same thickness or like little bit bigger thickness. So in this case, we call it hidden beam because you cannot see. Once you make the concrete casting, you will not be able to see. Usually this type of hidden beams would be wide beam and requires a lot of reinforcement because of the small thickness that it has. So you have drop beams, inverted beams, and also hidden beams. Okay, let's see what is the difference between rectangular and flanged sections. Okay, when can I design a section to be a rectangular section and when I should design the section to be a flanged section? Let's see here an example of a simply supported beam, supported into columns as you can see here. So under loads, you will see that at the top, you will have a compression force. At the bottom, you will have a tension force. So if we took a section here at this point, okay, so this is showing the cross section. This we call it the flange or the slab, and this is whole the beam. The beam, it has this part called the rib of the beam, and also this part in the slab is a part of the beam. So this is the beam and the flange. In this section, you will see that there is a neutral axis here. Above the neutral axis, you will have a compression force. Under the neutral axis, you will have a tension force. As you know, Most of the concrete design codes says that concrete will not resist any tensile forces. Once you have a tension force on the concrete, they assume that will be cracked and will not carry any tensile forces. So all the part here under the neutral axis, okay, we assume that it is already cracked. So once it is cracked, only the steel reinforcement will be carrying the tension force, and this part above the neutral axis where you have a compression forces will be carried by the concrete. So in this case, the flange is carrying compression force. The flange is carrying compression force, so we have to consider the flange in this case, and will be designed in this case as a flanged section. When you have a compression on the flange or on the slab, in this case, you will consider it and will be designed as a flanged section. So as a conclusion for that, if the flange is in compression, so we design this section as a flanged section. Okay. On the other case, if you have a beam, or this is part of the beam supported in a column here, and it extends, we just took only part above the column. In this case, under load, you will have the opposite. You will have tensile stresses at the top, and you have compressive stresses at the bottom. So if we took a section at this point here, so this is a neutral axis, but opposite to the previous one, you will have a tension force at the top and compression at the bottom. And as we said here, any concrete under tension will be assumed as cracked and will be neglected. So in this case, anything above the neutral axis here, it will be removed. Only I will have the steel reinforcements that will carry the tension force. So in this case, you can see that all the flange here is not carrying any load because it is under tension, and we assume that the concrete will not resist tension. So only the part here under the neutral axis, which is a rectangular part, as you can see here, is taking the load. The flange is not taking anything in this case, so we cannot consider the flange. So in this case, when we design the section to be as a rectangular section because the flange is already cracked. So as a conclusion also, if the flange is in tension, we design as a rectangular section. Okay, so in this case, the flange is in tension, so we designed this section as a rectangular section. However, in the simply supported here, as the spans, the flange is in compression, so we design it as a flanged section. Let's see here if you have a continuous beam. So using the same concept in the previous slide, we can see that, okay, in this beam, all these spans at the spans, okay, this tension will be down and the top will be under compression. So all of this will be designed as a flanged section. Okay. However, at the supports or above the supports here, you have a tensile force in the flange. So you will neglect the flange and will be designed as a rectangular section. Just be careful if you have an inverted beam, because if you have an inverted beam, the slab will be at the bottom. And in this case, it will be opposite to what we have here. Okay. But in most cases, you have the slab is a regular slab, the slab is above the beam, and in this case, above the support will be designed as a rectangular section, and the spans will be designed as flanged section. Okay, so it will come now the question, okay, if I want to design a section as a flanged section, what will be the width of the flange? Okay, what will be this B flange? For the section, we have B web. This is for the beam here, the web, and the top here, we call it B flange. How much it will be this B flange? According to the British standard, for T beams, okay, when you have flanges or flange from both sides, the B flange equals B web, okay, plus something called LZ over 5. We will see what is LZ in a few seconds. In a case, if you have a flanged section, but it is, we called it L beam when you have a flange only from one side. So the B flange in this case equals B web plus LZ over 10. So the difference between these T beams and L beams, here it is LZ over 5, and here it is LZ over 10. So in case of T beam, you have B flange is greater than the B flange in the case of L beam. So what is this LZ? LZ is the distance between points of zero moments. If you have a beam, let's say simply supported beam, so the bending moment LZ will be equal to the L because it's all positive moment from the support to the support. So the LZ in this case will be equals to the span, the L. In case of continuous beams, the LZ will be less because you have part is under negative moment, part is positive moment. So the distance between the zero moments will be less. So if you have a section in continuous beam, LZ will be taken as 0.7 L. If you have a simply supported beam, the LZ equals to L. Just you put the LZ here or this in this equation, you will be able to find the B flange. Okay. So how to transfer loads from slabs to beams? If you want to design a beam, you need to find the load on this beam, and then you make some structural analysis to find the bending moment and shear forces. Then you go for the design steps. So the first thing is to find the loads. Okay, you cannot find the bending moment and shear forces without finding the load. So to find the loads, usually beams are supporting different types of loads. Loads from the slabs, loads from walls, self weight of the beam itself. Okay, so first thing is the load from slabs. Okay, we have two different types of slabs, as we know. One-way slabs, when the Ly, the long side divided by the short side, is greater than 2. In this case, it is easy to transfer the load because for the one-way, we assume that the load will be transferred only in the short direction. So how to do that? We make a line here at the middle of the short direction, and then this part of the load above this line here will go to the long beam here. This part here, the bottom part, will go to the long beam. In this case, the short beams are not supporting any load from the slab. Okay, how to do that? We take this area here, and this is the beam that we are designing now. This is the beam. Okay, you have a support here, and this will be the area carried on this beam. Area 1 here, it will be the same area that you have it here. So how much is the height here? The height, it will be equal to the Lx over 2. The short span divided by 2, because we always divide the short span. Okay, so if you want to find the load here, okay, it is easy. If you have a load on the beam N or W equals any value kilonewton per meter square, this is the load on the slab, total load. So how to find the load on the beam kilonewton per meter? So it equals this length, this height here multiplied by N. So the W equals N kilonewton per meter square times length per meter. So it will be only kilonewton per meter. So this will give you the load. Once you have the load here, kilonewton per meter, you will be able to get the concentrated load. If you want to get the resultant, you can get the reaction, you can draw the shear and the bending moment in this case. So in one-way slabs, it is easy. All the load will be going to the long beams because the loads goes in the short span of the slab. So it will go to the long beam here, the long beam here. This beam and this beam will not take any load from the slab. How about two-way slabs? In two-way slabs, you have the Ly over Lx is less than or equals to. So how to transfer the load in this case? First of all, you have to make inclined lines at 45 degrees from all the corners, and then they will meet, intersect at one point. Then you connect these 2 points. You can see here that you will have part will be like trapezoid, the loads, and you have triangle loads, as you can see. For the trapezoidal load, this part at the bottom will go to the bottom beam, the bottom long beam here. The top trapezoid will go to the top long beam, as you can see. And then you have triangle part will go to the short beam. How much is this height here? It is always Lx over 2. The same here, because this is 45 degrees, the angle. So this distance equal to this distance. So the height here, it is Lx over 2. The height here, Lx over 2. How much is this distance between this point and this point? It equals Ly minus Lx minus Lx. So it is Ly minus 2 Lx in this case. So for the bottom beam here or the top beam, the load will be this area 1 will come and will be supported in the bottom beam. And as I told you, the height will be Lx over 2 to get the load here as kilonewton per meter. So again, it will be N times Lx over 2 to something kilonewton per meter. Once you have this one, you will be able to get the bending moment reactions and shear forces. Okay, then for the short beam, it will take always a triangular load, as you can see. and this will be area 2, and the load again, it will be the same load here because both of them, they have the same height, Lx over 2 and Lx over 2. This is showing to you how to transfer the load in case of one-way slab to the beams and for two-way slabs. For one-way slabs, again, the load will be transferred only to the long beams. Short beams are not taking any load from the slab. It may take a load from a wall, the self-weight is still there, but load from the slab, it is neglected and all the load will be transferred to the long beam. In case of if you have two-way slabs, you know that all beams will carry loads because the loads in the slabs will go in both directions, in the short direction of the slab and in the long direction of the slab. So all beams will take loads. The long beam will take a trapezoidal load, and the short beam will take a triangular load, as you can see. If you have here a square slab, everything will be triangles, and in this case, you will not see trapezoidal load. Okay, in continuous beam, the bridge standard is giving a table 3.5, that can be used to design for or to find the ultimate bending moment and shear forces, but under some conditions. Okay, we cannot use table 3.5 unless we satisfy the following three conditions. First, the live load on the beam should be less than or equals to the dead load. Okay, live load should be less than or equals to the dead load. The second point, loads should be uniformly distributed over three spans or more. So we have to have uniformly distributed load, and the spans should be three spans or more. You cannot use this table 3.5 when you have only two spans, okay? Because the minimum is three spans or more, okay? You cannot use table 3.5 if you have a concentrated load on the beam because it's saying uniformly distributed load. Also, the live load should be less than or equals to the dead load. What will be the third condition? The third condition, variations in the span length shouldn't exceed 15% of the longest span. So the span should be somehow close to each other. 5 meters, 5.5, 4.9. Okay, the difference between the span should be less than or equals to 15% of the longest span. Because if you have big difference, this table 3.5 is not going to give you accurate results. And in this case, your design may be wrong and is not satisfying the requirements. So in this case, if to use table 3.5, you should satisfy the three conditions. What is this table 3.5? Let's see it together. It is similar to the table that we saw when we were designing continuous one-way slabs, but with a little bit difference in the values. So you have the first row here is for the bending moment, the bottom row is for the shear. And you can see here at the outer supports assumed as 0 because assumed like as assembly supported at the end, or the connection between the beam to the column will be as assembly supported. Near the middle of end span, it is of course positive moment 0.09 F capital times L. At first interior support, it will be negative minus 0.11 F capital L. Middle of the interior span would be 0.07 FL, and then at interior span again it will be negative, and this is showing the shear forces. Of course, the shear will be at the supports. The shear at the spans or near middle of the spans will be always minimum. So it is similar to the table 312 in the bridge standard that we use to analyze simply supported one-way slabs, and also similar conditions were applicable there. So what is this capital F here? Capital F is the total design ultimate load, okay? The resultant of the load, not the uniform load. It's equal 1.4 G capital K plus 1.6 Q capital K. Capital and capital here means the resultant of the load, not the uniform. So if you have a uniform load, you should multiply this uniform load by the span to get it as a resultant force. It is the capital F, okay? L, of course, is the effective span. And as we did for the slabs, if you have a first interior support, if you have a span on the left and the span on the right is not similar, so you have to take the average here from both values. So it will be minus 0.11 times F1 L1 plus F2 L2 divided by 2. You get the average from both sides. Okay, let's see it here more clear. If you have a span L1, span L2, span L3, or whatever, So you have to first to get the resultant of the load as F capital 1 for the first span, F capital 2 in the second span, and then you will be able to apply table 3.5. So for the bending moment at the beginning assumed as 0, here you will have a positive moment, positive 0.09 F1 L1. Then at the second span, again, it will be positive here, 0.07 F2 L2. At first interior support, it will be minus 0.11, and you get the average from both sides, F1 L1 plus F2 L2, all divided by 2. And then you continue. If this is continuous, you continue as a second here. If this is continuous here, it will be the interior support and so on. Then for the shear, also we'll use the table 3.5, the bottom row. It is 0.45 F1, not multiplied by L in this case, minus 0.6 F1, then 0.55 F2, and so on. If you have an end span here like this one, again, you will use the same values that you used at the first span, because first span from left or first span from right, they are the same. This 0.45 F, 0.6 F, assuming that we have here F1 is similar to the F1 that we have it here. Okay, so this is showing how to apply table 3.5 here in the British standard to find the bending moment and shear forces in continuous beams satisfying the full B3 conditions. Okay. So now we are ready to go to the design steps of beams. This is section 3.4 in the BS8110. First thing, we have to make initial proportioning. Initial proportioning, it means I need to find the dimensions. Okay, what will be the total height of the beam? What will be the thickness of the beam? Okay, we need to make initial proportioning because everything in the design will be depending on the depth, the B web that we have it, and also it will affect the self weight of the beam. Okay, so we have to estimate the effective depth. Okay, D. Again, we use table 3.9 in page 215 in the BS, but in this case, we use here, usually we are designing flanged beams. So usually we are using this one, B web over B is less than or equals 0.3. So in this case, if you have assembly supported, this will be the factor 16. Continuous, this will be the factor. But in this case, we don't divide by modification factor. We take the value here. So to find the depth, basic depth or the minimum depth, it will equal to the span divided by these factors. Okay, it will give you an initial value, but now round it up, always round it up to be in the safe side. So the same table here, but don't use any modification factor that we used in the case of slabs. Okay, so this is the first step to get the D. Okay, then we have to estimate cover. Okay, we have to estimate the cover to the steel. It will be the larger from two values, durability, table 3.3. Okay, this is exactly similar to what we did in case of slabs. This table 3.3, it will give you the nominal cover to all reinforcement, including lengths to meet durability requirements. And it depends on the exposure condition, mild exposure, moderate, severe exposure, very severe, and so on. And also it will be affected by the complete compressive strength. So if you have, let's say, a severe environment, you can see that in this case, we cannot use concrete less than here. Dash here, it means you cannot use concrete 30 and concrete 35. So in a case of severe environment, you have to use a better quality concrete with BC40. And from here, you can find that this will be the cover. Let's say you have a mild exposure, and in this case, you can use, if you have a concrete 30 megapascal, the cover will be 25. If you are using concrete 35, of course, the cover will be less and will be 20 in this case. So using this table is exactly similar to what we did in case of slabs. And if you want more, you can go and check my videos about one-way slabs and two-way slabs. This is for durability. Now the second check for the cover, it will be about fire resistance. We have table 3.4. This is the same table here. And at the first column, you have the fire resistance per hour, half an hour, 1 hour, 1.5, 2, 3, and 4 hours. And here it will give you the cover that you need based on which structural element you are designing. In floors, you have to use the one with floor simply supported or continuous. In a case of you are designing a beam as we are doing in this video, so we have to use the values here. In a case of simply supported beams, it will be these values. In a case of continuous beams, it will be these values. You can see here the difference is almost no difference from 0. Half an hour to 1.5 hours. After that, you can see there is a difference between a simply supported and a continuous. So once you calculated the cover from durability, the cover from fire resistance, you will take the larger from both of them. This will be the cover that you are going to use. Then to find the total H equals D, the effective depth that you calculated from table 3.9, plus cover, the larger from these two values, plus what? Plus phi bar divided by 2, half diameter, plus phi length. In the beams, we have an additional length, which was not there when we were designing for slabs. So for beams, we increase here phi of the length. So as a guide, for the phi of the link, assume it as 10 millimeter, sometimes 12 millimeter. It's okay, it's up to you. Assume it 10 millimeter. And for the diameter of the bar, in this case, we assume it 20 millimeter because usually the size of the bars in the beam is greater than the size of the bars in the slabs. In the slabs, we used to assume the phi bar 10 millimeter. However, for the beams here, just assume it 20. So substitute these values into here, you can get the H. Okay, usually this H from table here, it depends on D, and it is like little bit smaller value. So always round H up, okay? Round it up to the nearest 50 millimeter, okay? And keep in mind that the H minimum will be 300 millimeter. So if you have the H is less than 300 millimeter, take it as 300 millimeter, okay? If it is greater than 300 millimeter, it is fine, but always round it to the nearest 50 millimeter. So if you have 300, the second one will be 350, then 400, 450, and so on. So always it will be better for the workers in the site to go with 50 millimeter, nearest 50 millimeter, 5 centimeter higher for the beam. So the H will be 300, this will be the minimum. Then you will go 350, 400, 450, 500, and so on. Okay, so this will be the H. Now, you need to find the width, how much it will be the width of the beam. Normally, the width will be ranging between h over 3 to h over 2. Okay, from h over 3 to h over 2, and round it to the nearest 25 millimeter. Okay, we round to the nearest 25 millimeter. Also, you may take another h, which is not similar to this, because another b, sorry, because this width of the beam is usually you have a wall under the beam. So sometimes we keep, or like it is preferable to use to keep the same width of the beam as the same width of the wall under the beam. Okay, so if you have a wall of 25 millimeter width, okay, this is the thickness of the wall, so it is better to use the same thickness of the beam. Okay, don't use a smaller thickness or a smaller b of the beam than the wall under the beam. But we may use a bigger b than the wall. If you have a wall of 10 centimeter only, okay, 100 millimeter, okay, in this case, you may use a 20 millimeter width beam or 25 to be able to put your reinforcement, because making a beam with 10 centimeters will be very small. Sometimes it will be difficult to put your reinforcement inside. Okay, so don't use a beam with a b less than the wall under the beam, but you can use it bigger than the wall thickness. Okay, and always round it to nearest 25 millimeter. Once you calculated the h, okay, and because we rounded, so we have to recalculate the d. Again, the d, it will be using the same equation here. You can use the d, take the d from the other side, it will be equal to h minus cover plus phi length plus phi bar over 2. By doing that, so you finish the initial proportioning, you know the h, and also you know the beam. So you are ready now to go to the second step about final proportioning. And always final proportion is starting by calculating loads. So we start by the dead loads. In this case, dead loads, we have different types of loads. Usually we have it on the beams. The first thing is the self weight of the beam. Okay, the self weight of the beam. Self weight of the beam equals H minus HF times B times gamma times L. Okay, what are these values? It will be the cross section of the beam. Okay, we need to get the volume multiplied by density, okay, by the total length of the beam to get it as a kilonewton. So the cross section, it will be H minus HF, because this HF is the thickness of the slab. It is already considered in the slab, no need to repeat it. Okay, so H is the total height of the beam minus H of the flange, okay, multiplied by the B web multiplied by gamma. This will give you, this part here will give you per meter. If you want to get it as for the total length of the beam multiplied by the length, it will give you as kilonewton. Okay, this will be the self weight of the beam. Then we have dead load from the slab. Dead load from the slab equals dead load multiplied by the area supported. Okay, if you have an area of the slab supported on a beam, so you have this area, it is meter square multiplied by the load kilonewton per meter square, it will give you as a load in kilonewton. This will be the dead load from the slab. If you have walls on the slab, if you have walls, not partitions, like real walls on the beam, supported on the beam. So again, you need to consider that, because usually it will be like heavy walls. To do that, it will be similar to the self weight, but in this case, we get the self weight of the wall. It will be the width of the wall times height of the wall times gamma times the span. Again, it will be kilonewton. So it is repeated of this one. Okay, the height of the wall, it is similar to the height of the beam H minus HF. Width of the wall, it is similar to the here B. In the case of the self weight of the beam, it is B multiplied by gamma multiplied by L. But in this case, the gamma of the wall should be taken into consideration, and the density of the wall, it depends on the type of the walls that you have. If you have hollow blocks, if you have solid blocks, what is the type of the material that you are using, lightweight or heavyweight, and so on. So based on the type of the wall, you have to know how much it will be the gamma of the wall. However, for the concrete, we use the gamma for the concrete, which is usually 24 kilonewton per meter cube. So if you calculated the self weight of the beam, kilonewton, dead load from the slab in kilonewton, wall load as in kilonewton, to get the total dead load, you get the summation of the three values here. Self weight, slab load, and wall load, it will be as kilonewton. Okay. Now you need to add the live load. Live load, from only live load, it comes from the slab. So it will be the live load multiplied by the area supported, area of the slab supported on the beam. It is similar to the dead load, but in this case, we, instead of using the dead load, we use the live load. Okay, so usually live load is kilonewton per meter square. It could be 2 kilonewton, 3 kilonewton per meter square multiplied by the area supported. And in this case, you will get the load as kilonewton. Once you have the total dead load and the total live load, in this case, it will be able, you will be able to get the total load, ultimate load in this case, will be 1.4 times dead load plus 1.6 times live load as a kilonewton. This is still kilonewton, okay? So this is the resultant of the load. If you want to get the load as kilonewton per meter as a uniform load, you need to divide this total load here per the span of the beam, okay, the L. So if you divide the total load, kilonewton, divided by the span of the beam, it will be as kilonewton per meter as a uniform load on this beam. And in this case, you will be able to use this uniform load to make your design. Okay, usually you do this in a case of continuous beams. In a case of simply supported, it's easier to do that with the trapezoid load or the triangle load, as we saw together. Okay, once you have the loads on the beams, you go to the step of the structural analysis. Structural analysis for continuous beams under uniformly distributed load, we can use table 3.5 that we saw a few minutes ago. In this case, you will be able to find the moment and to find the shear. Once you have the bending moment, you will calculate for the reinforcement, as usual, section 3.444. It always start by calculating the K equals M ultimate divided by FCU B D square. You calculate the Z, you calculate the AS required, and then you will be able to get the area of the steel. You can do this manually, the number of bars and the diameter, or you can use this table here, table number 1, that help you to get the number and diameter directly. So let's say you have an area of steel reinforcement of 900 millimeter square. Okay, 900 millimeter square. So you can choose, let's say, if you choose 16 millimeter, okay, and this is the number of bars. So one bar, it will give you 201, two bar, three bars, and so on. So 800, we said if you have 900 millimeter square, so it will be between 4 and 5. In this case, you will use 5 T16, 5 bars of diameter 16. Or if you want to use diameter 20, so it will be 3 bars diameter 20, or 2 bars diameter 25, and so on. Okay. For beams, don't use a diameter less than 10 millimeters, and in practice, we don't go less than 12 millimeters for beams. Okay. In practice, we don't go less than 12 millimeters for beams. For the slabs, usually we don't go less than 8 millimeters, but also in practice, it is better to use 10 millimeters and above. Okay. So this is showing you how to get the number of bars and diameter of bars. And once you did that, you will know how much is provided. You finish the design, but you still need to make some checks. Okay, so you have to check deflections using the largest span moment, the maximum positive moment from table 310, which is the same table that we used for checking deflections in slabs. Okay, the same here, you have to check your modification factor. It depends on something called the FS, the stress in the steel reinforcement, and M over BB square. FS, you can get it from this equations here, 2 over 3 F yield times AS required divided by AS provided, and beta B always we use it as 1. Then M in this part here, always the M that we use it is the maximum positive moment. Maximum span moment means maximum positive moment. B and D is B web, and D is the depth of the beam. So this is the same equation and the same modification factors that we use to check deflection in beams and slabs. Okay, if the deflection is safe, then you have to design for shear. Okay, not only check for shear. In slabs, we check for shear because usually you don't use stirrups or shear reinforcement in solid slabs. But for beams, you have to use links or stirrups. So we have to design for shear. Left and right of each support, you will have different value. So you have to check that. And then you design based on table 3.7 and table 3.8. Let's go and review together. Table 3.7 in the BS code, it tells you if the shear stress is greater than zero point 0.5 VC and less than VC plus zero point 0.4, where VC is the shear stress carried by the concrete. In this case, you use minimum lengths. Minimum lengths, you can get the area of the minimum lengths from this equation here, ASV minimum. If you have the shear stress is greater than VC plus zero point 0.4 and less than the maximum shear, which is the minimum of 0.8 square root FCU or 5. In this case, if it is between these two values, you have to design for shear reinforcement. And in this case, you design using this equation. The difference between this equation and this one, here we use only 0.4, but here we use V minus VC, which is greater than 0.4. If you have a case that the shear is greater than the V max, in this case, you cannot design for shear. The only choice that you have in this case to increase the dimension of the beam. You have to increase the cross-section dimension. You can increase the B, you can increase the depth in this case, but you cannot design because it would be unsafe even if you put a lot of shear reinforcement. This is table 3.7. And also table 3.8, it tells you how to get the VC, okay? How much is the shear carried by the concrete? We use it from this equation, 0.79 times 100 AS divided by BV D to power 1 over 3 times 400 over D to power 1 over 4 divided all by gamma M, and gamma M in this case is 1.25. And keep in mind that 100 AS over BV times D should be taken as greater than, shouldn't be taken as greater than 3. So the maximum for this value will be 3. And 400 over D should be greater than 1. If it is less than 1, you take it as 1. If you have a concrete strength of greater than 25 megapascal, all the values here, or this value should be multiplied by FC divided by 25 to power 1 over 3. This is again repetition of what you have taken in shear checks for slabs. It is the same equation applied for slabs and applied for concrete. From this table, we get the VC. From the previous table, we get we design for the shear reinforcement. So table 3.7 and table 3.8 for each span design the required shear reinforcement. And when I am talking required shear reinforcement, means you need to know the diameter of the link and the spacing between links. Okay. Then once you did that, you have to check cracking from table 325 and section 312 11 2. From table 325, it will give you the minimum percentage of reinforcement. Okay, you have here for flanged beams when the web in tension, for flanged beams when the flange is in tension. Okay, and you have different values here based on the steel that you are using. Usually we are using a steel or high yield steel, so these are the values. You have different values here. It depends on which type of beam you are designing. If the flanged beams and the web is in tension, okay, it depends on the B web divided by B. If it is less than 0.4, greater than or equal to 0.4, so you have a value of 0.18% or 0.13%. For flanged beams and the flange in tension, like it means like a rectangular flanged beam, but the flange is tension, so it will be designed as a rectangular section. So if T beam and L beam, you have here also some values. Okay, let's go back. How about this section, section 3, 12, 11, 2? Let's see together. It gives you also the spacing of reinforcement, minimum distance between bars. Okay, so the minimum distance between bars in a case of beams, it is equals the bar size. When the bar size exceeds H aggregate plus 5, a spacing less than the bar size or equivalent bar should be avoided. Okay, what does this mean here? Okay, like the conclusion of this part, it tells you that the spacing between bars should be taken greater than or equals to H aggregate plus 5 millimeter. H aggregate is the aggregate size that you are using plus 5 millimeter to allow you to have an enough space for the aggregate to go between the steel bars. Usually we take this as a minimum of 25 millimeters, H aggregate plus 5 millimeter. Okay. Also, if the bar size is greater than the H aggregate plus 5 millimeter, in this case, it will govern the spacing, and in this case, take it greater than the bar size. So it is the spacing will be between the bars, the minimum spacing will be the maximum of two values, H aggregate plus 5 or the phi of the bar. Okay, which one is greater, you take it. Also in the vertical distance between the bar, if you are using more than one layer, also the vertical distance between bars shouldn't be less than 2 H aggregate over 3. Okay, 2 H aggregate over 3. And usually we take it also similar to the phi diameter or 25 millimeters. Okay, how about the maximum spacing? Also, we have a maximum spacing between bars. The maximum spacing in a case of 460, if you assume no redistribution, so the value will be 155 millimeter. So we have a range of the spacing. The minimum will be H aggregate plus 5 or phi diameter, which one is greater? And usually this is about 25 millimeters. Okay, and the maximum spacing between bars shouldn't exceed 155 millimeter in a case of 460 steel, high yield steel you are using. Okay, so between 25 and 155 millimeters. Then once you did that, you have to make your drawing and detailing of the beams, longitudinal section and the cross section at mid spans and at support. And we have figure 324 in the code that shows how to do this. Let's see here together, like modification of this drawing or this drawing to make it easier for you to understand. In a case of simply supported beam, the code is allowing you to cut 50% of the bars and extend 50% of the bars. So if you have here 100% at the middle because you have the maximum moment here, so it allows you to cut 50% of the bars. And what will be the distance here? The distance from the center line of the column to this cut, it is 0.08 L, where the L is the span from center line to center line. So this is in case of simply supported beams. In case of continuous beams, also here, it allows you to extend 30% of the bars and you can cut 70%. And the distance here will be from the end support L over 10 or 1L, and from the middle support it will be 0.15L. Usually we cut 50%, 50%, but the code is allowing you to cut 70% and extend 30%. The top reinforcement here, okay, above the support, you will have the required reinforcement because this will be a negative moment here and you have a high tensile stresses. So it allows you to cut the part of the bars here, 60% here will be extended to a distance of span over 4.25 of the span, but from the face of the beam. Then if you want to cut another part of the bars, okay, the minimum distance here, it will be 0.15 L, 15% of the span, again from the face. So for the top reinforcement, the distance is always measured from the face of the beam. For the bottom reinforcement, the distance is always measured from the center line of the beam. How about this reinforcement here, which is 20%? This is hangers. We call them hangers. Theoretically, you don't need reinforcement here because you don't have tensile forces at this part or this part of the beam, but you need some reinforcement, minimum reinforcement for shrinkage, for temperature changes, and also for hanging the links, because you have stirrups, and this is why we call these types of bars hangers. And this bar is always taken 20% of the bottom steer reinforcement. Take it as a minimum, 20% of the bottom steer reinforcement. So if you have here, let's say 10 bars of a diameter, you take 2 bars as minimum. Okay, you can increase, yes, you can increase than 20%, of course, because 20% is the minimum. For the cantilever also, you can extend 50% will be with the whole length of the cantilever. Another 50% will be shorter, where this distance is the greater of L over 2, the span over 2, or 45 times bar diameter. So this is showing you how to make curtailment of the steer reinforcement, how to cut your steer reinforcement according to the bridge standard. Also at the end anchorage, at simply supported here, at the end here, you have this steel bar. It is under tension because it has a tensile stresses at the middle of the span. So how to extend? What will be this distance from the center line to the end? It is beyond 12 times bar diameter. If you have a bar diameter here, it's 5, okay? So this distance from the center line to the end of the bar, it is 12 times bar diameter. So what if this distance is not enough? So you have to bend the bar. We have to use some hook here, 90-degree hook, and we bend the bar to extend and to satisfy this requirement by the code. Also, beyond the face of the support, this distance from the face here to the end, should be greater than d over 2 plus 12 times bar diameter. Okay, so you have to satisfy these two values. Usually this will be enough, and usually this distance is not, you will not be able to satisfy this requirement. So we use a hook, a 90-degree hook, and we extended this bar a little bit up to satisfy this requirement. Okay, additional reinforcement in the beam. So the code also is have some requirements about transverse reinforcement in flanged beams. This transverse reinforcement, it means the reinforcement above the beam, this reinforcement in the slab. It is telling us that this reinforcement as a minimum should be taken as 0.15% of the cross section of the flange. 0.15% of the cross section of the flange. If you did that 0.15%, 0.15 divided by 100 times 1,000, if you assume like 1 meter width of the flange, we take 1 meter because it's a slab, times h. So this will give us a value 1.5 HF. Okay. If you still remember the minimum reinforcement ratio in the slabs, it was 0.13%. Okay. Here we have a special requirement above the beam. The minimum reinforcement in the slab above the beam shouldn't be less than 0.15%, which is a little bit greater than the minimum of the slab. So you should be careful in this part and increase little bit the reinforcement to satisfy this requirement. Okay, AS should be greater than or equal to 1.5 HF or 0.15% of the area of the slab. Also, side reinforcement in the beams. If you have a beam here with H is greater than 750 millimeter, if this H is greater than 750 millimeter, so the code is requiring to put something called side bars. These are side bars. It's not allowing to have only top reinforcement and bottom reinforcement. We should have some sidebars here. This is only in case if H is greater than 750 millimeter. So in case of H is less than 750 millimeters, not required to put these sidebars. But if it is greater, you should put sidebars. Okay. How much is these sidebars? Okay, it tells us the spacing between these sidebars shouldn't be less than 250, should be less than or equal to 250 millimeter. Okay, so if you are using sidebars, the spacing SB, okay, should be less than or equals to 250 millimeter, and it will cover 2 over 3 of the total H of the beam, 2 over 3 H. We have to use sidebars here. Spacing should be less than or equals to 250, and the diameter of these sidebars here should be greater than the square root of B times SB divided by F yield. F yield is usually 460, B is the B web, and SB is the spacing. So based on the spacing, you can choose the diameter, or based on the diameter, you will be able to get the spacing between these sidebars. Okay, by doing this, we reached the end of the first part of the presentation. We will have two other videos. One video about design example of simply supported beam, another video which will be part 3. It will be of